then we know that basically the y value is below the x-axis. If f of a is equal to 0, we know, because we've made this far math, that means we are on the x-axis. And if we say that f of a is not defined, then we basically just know that there is no closed dot at x is equal to a. And of course, that could be lots of situations. It could be a hole, it could be a jump, it can be an asymptote, but we just know that the graph does not exist at a. If I just provide you with that bit of information, so like if I just say, hey, this graph is above the x-axis, we don't really know what else the graph looks like. Like it could be increasing, it could be decreasing, like we don't know. We just know it's above the x-axis. So for these second two columns, we're just going to put like a question mark here. Not that we'll ever go back and fill it in. We just don't know what it looks like. We don't have enough information, basically. For that fourth row, though, if you don't have a function there, we talked about yesterday how if the function isn't there, then it can't have a first derivative. So the function doesn't exist, then the first derivative is not defined. And then even though we haven't really talked about what this second derivative represents, if you don't have a first derivative, then you also can't have a second derivative. But there's not really any calculus in those first four rows. We just are talking about the y value of the graph. Where the calculus is going to come into play is going to be in these next four rows. And this will be kind of a good review of yesterday. So yesterday we talked about the first derivative, and we saw four cases of what that first derivative could be. That first derivative could be positive, that first derivative could be negative, it could be 0, or it could not be defined. What did we know the graph was doing if your first derivative was positive?
Increasing.
It's increasing. So in that second column, if f prime is positive, then f is increasing. So then we also remember if f prime is negative, then f is decreasing. And so when I talk about increasing or decreasing, let's really think about what that means in math. Like we know that means it's basically going up from left to right. But in math, functions actually have three different ways they can increase. They can increase with like linear growth. They can increase kind of like an exponential and bend upwards. Or they can increase like a log or a square root function with a bend going down. So we basically have three different shapes of a graph that all could be types of increasing functions. Same with decreasing. It can decrease in a straight line. It can decrease bending upwards, or it can decrease bending downwards. But those are really the only three options you have. Like it could be steeper or more dramatic, but those really are only the three options we have for increasing or decreasing. What did we say yesterday it meant when the derivative is equal to 0?
It's the tangent line is horizontal.
The tangent line is horizontal. So we're going to say that f has a horizontal tangent at x is equal to a. So do want to be clear, if the derivative is equal to 0, the whole function could just be horizontal. It could be a horizontal straight line, but more likely it's a part in the graph that just has a horizontal tangent. Different ways a horizontal tangent can show up. It could be a spot where the graph is like changing direction, so like at the vertex of a parabola, or it could just be at the part of the graph that flattens out for a little bit, so like in a cubic function. But anytime the tangent line is horizontal, that means that the first derivative is equal to 0. And then we also talked about three cases where a derivative was not defined. And those three cases we had was, of course, a cusp, a discontinuity, or a vertical tangent line. A cusp is, of course, when you have a sharp turn in the graph. Discontinuity, we've talked about that enough, so that can be anything from like a hole, a jump, or an asymptote. And then a vertical tangent is when the graph actually has a portion of the graph that turns completely vertical. So kind of like a cube root function would have a vertical tangent. How we're going to describe what it means, if I say f prime is not defined, that means f does not have a derivative. The way in calculus we're going to say that f does not have a derivative is we're going to say that statement as f is not, and we're going to use a new word, it's differentiable. So when I say not differentiable, that means that it does not have a derivative at that particular point. And so you might be asking, well, what about the second derivative we keep talking about? Similar to that row, the rows above it, if I just give you information about the first derivative, we can't kind of move forward and know things about the second derivative yet, just based off of that description. So before moving on to actually talking about the second derivative, does anyone have any questions on the first kind of 2/3 of that chart that I should go back and explain a little bit better? All right, so let's go ahead and move to the last 4 rows. This, I think, is probably the only really bit of new information besides that phrase, not differentiable. And of these last 4 rows, really the most important ones are going to be the first 2 in that last set. And this is going to be when we're talking about the second derivative. And so the second derivative deals with something called concavity, which is basically talking about how the function bends. And just like the first derivative, the second derivative can be positive or it can be negative. If the second derivative is positive, then we're going to say the graph is concave up. If the second derivative is negative, we're going to describe that as concave down. I will often in this class abbreviate those, and you're more than welcome to as well, because we'll use them a lot. Concave up, CC up arrow, concave down, CC down arrow. And so now you're asking yourself, what does concave up or concave down look like? Concave up is going to be anything that makes like a bowl shape is how I think about it. Something that bends upward, something that will like hold water or be like a portion of a bowl. So some examples of a concave up function would be something like I could just have an increasing in concave up function. I can have a decreasing in concave up function, or I can have a function that increases and decreases and is concave up. Notice for all these, it's bending upwards and kind of making like a bowl shape or part of a bowl shape. Concave down, on the other hand, to me, I always think of those are going to look like an umbrella. They're bending downward. So you can have something that is increasing in concave down, something that is decreasing in concave down, or a function that increases and decreases and is concave down. So when we're looking at these, we can kind of visually see they're all bending downward, and that's what I mean by concave down. And so using this information together, we can actually describe a function better. Instead of just saying, hey, it's increasing or decreasing, now we can say, hey, this is increasing and concave up, which gives us a better idea of what that function actually looks like. And these have tons of other applications even outside of math, like in physics and other types of situations that we'll look at pretty much all this first semester. So then I do want to go ahead and fill in the other 2 blanks on this row, and I'm going to highlight them because I have found if students are going to mess something up, it's going to be these 2 boxes. I think because it's not always intuitive to think about, but it's how the first derivative relates to concavity. And so if I say the second derivative is positive, that does mean the function is concave up, but we're going to describe that as being f prime is increasing. Also, if I say the second derivative is negative, that means the same thing as saying f prime is decreasing. And I'm going to give you some examples about why that is the way it is, just so it helps make a little bit of sense to you. But I do want to pause and kind of talk about being very clear and distinct with our language in this class. So in math classes in general, like mathematicians are not known for writing like long essays. Mathematicians like to be short, clear, and concise. So to help you with that in this class, and also so you don't lose points on the AP exam, I would try to avoid the word it as much as possible. So instead of saying things like it is decreasing, you want to say things like f prime is decreasing, or you want to say the function is decreasing. So you want to be clear about what is actually decreasing. You also want to make sure you keep things separated in your head. Saying something is negative is not the same thing as saying something is decreasing. Those are two separate meanings. One's talking about like the value of it. The other one talks more about like what it is doing. So like something could be positive and decreasing. It can also be negative and decreasing, and those mean different things. So what I'm talking about in these rows, to like be a little bit more clear, I'm gonna go off to the side. In that first row, basically what I'm saying is if you know f prime, f double prime is greater than 0, then you also know first that f prime of a is increasing, and you also know that f, the function, is concave up. All three of those statements are interchangeable, but notice we're not saying like f double prime is concave up. We're saying since f double prime is positive, that means f prime of a is increasing and f is concave up. And of course, I can write a similar statement if I have f double prime is less than 0. The part I do want to look at is, well, how does an increasing first derivative make the graph concave up? Some students are more than happy just to be like, all right, Mr. Brown, I got it. I'll just memorize that that statement means concave up. I do think having a visual is nice to kind of think about why it's actually concave up. So if I just make a random t-chart and I have x as my input and my derivative as my output, and again, I'm just making this up, so my x's I'll say are like 0, 1, 2, 3, 4. And if I say f prime is increasing, I'm just going to go ahead and start with a value and keep going up. So we can agree that those numbers in f prime are increasing. They're getting bigger as you go across. Well, we know the derivative does just represent slope. So like a slope of 1, I'm going to estimate it looks something like this. A slope of 2 is a little bit steeper, 3 is a little steeper, 4 is even steeper, and then 5 is pretty steep. If I put those points together on a number line, so I had at x equals 0, the slope was 1. At x equals 2, the slope, or x equals 1, the slope was 2. And then the slopes get steeper. You can see that it does bend upwards. Same thing if I expand that, if I say that f prime is decreasing. So if I want to think of some decreasing derivatives, just to give you a visual, so like if I have x and f prime, and just to show you it works if I deal with negatives as well. So if I start off with a slope of 2, 1, 0, -1, -2, those numbers are decreasing. So if I go to draw those slopes, again, this is just to prove to you that a decreasing first derivative means it's going to be concave down. So I have like a slope of 2, a slope of 1, a slope of 0, a slope of -1, a slope of -2, and we can see that it is bending downwards. So there's the reason why it works. Again, if you don't care about the reason, just know this chart, memorize this chart, live by this chart in this class. The last two rows are not as important. I am going to go ahead and fill it in for you just so you have it. But if I tell you that the second derivative is 0, then that does mean that f prime has a horizontal tangent. But without more information, you can't really know what the graph looks like if you say it has a 0 second derivative. Like when we start having functions, we can, but right now we can't. Same thing if I just tell you that f double prime is not defined, like no clue what the graph looks like, but we can visually describe that as, well, if there's no second derivative, then you can say like f prime is not differentiable. And if f prime is not differentiable, then kind of moving backwards, you can say f itself is not twice differentiable. And when I say twice differentiable, that just means you can't take the derivative 2 times to even find a second derivative. Again, I'm not too concerned with those last 2 rows right now. The most important part of that chart are going to be those first few ones. So at this point, I know I have some examples, and some of you could probably do them without my direction right now. But is there anything on this chart you want me to go back and explain, especially anything with the rows dealing with the first derivative and then those first 2 rows dealing with the second derivative?
On the f double positive, like when a is positive, how is f prime increasing if, like on that second graph example, wouldn't it be decreasing at that point?
So you have to make sure, like you keep in your head, there's a difference between saying something is decreasing and something is negative. So in this second graph that I drew, like in this first section I highlighted, so that I put in yellow, how I would describe this, like I could say f prime is decreasing and positive. It's f prime is decreasing because it's concave down, but it's positive because the graph itself is increasing. But on the other side of 0, f prime is still decreasing because it's concave down. But instead of decreasing, it's now negative. So you have to kind of keep separating your head. When I say decreasing, that's not the same thing as saying it's negative. So we're going to have to keep those words kind of separated when we're talking about these graphs.
So the L shape would be increasing but negative?
Say it one more time.
So the L shape would be increasing but negative?
Where am I looking at? Sorry.
The concave up. I think that's what he means.
Yeah, the
I'm confused.
L-shaped
yeah.
graph.
Oh, the L-shaped one. Okay.
Yeah,
Thank you for
that one
helping
is
me.
confusing.
So if I'm looking at the second one, like I didn't have any negatives in here. So this whole graph, based off of how I have it drawn, I have, yeah, so it would just be f
No,
prime
Mr. Brown.
is increasing and positive.
The concave up, the 3 pictures you showed, the one in the middle. That's what we're confused about.
Okay.
Yeah, the middle one on the concave up. How is that increasing?
On the concave up. Oh, the L-shaped one.
Yeah. How is that increasing?
So that one, we're going to say f prime is increasing because if you think about the slopes, okay, I got it now. Thank you. So on the L-shaped one, I'm just going to kind of draw it over here. So if I have a graph that looks like this, again, let's just estimate the slopes for f prime. And so when we're thinking about this one, it is concave up, so we know that f prime is still increasing. So you think like this is a very steep slope, so I might say the slope is like -10. Over here, we can kind of see the slope is at 0. The slope here looks like it's at -1/2. And I'm just like making up these numbers. So I made up those numbers, but basically you kind of see like it starts off being very steep and negative. And if you keep going across, as it gets flatter, yes, they're still negative, but those numbers are increasing. So we can still talk about that f prime, the slopes are still increasing because we're concave up. Maybe this helps. When I say f prime is increasing, you can also think of that in like non-calculus terms as like the slopes are increasing in value. Does that help?
Yeah, that helps.
Okay. So what I want you to do, and this is what your homework looks like tonight, is basically making sure you understand this chart. So homework 7 is just one page of a bunch of graphs that look like this, where I give you 2 pieces of information, and I want you to draw a possible graph that matches that situation. So if I'm looking at this first one, there's 2 statements here. If I say f of A is greater than 0, what's the only thing that is telling us about our graph?
It's above the x-axis.
Above the x-axis. At A, to be clear. And then if I see f prime of A is less than 0, what does that mean about your graph? If f prime of A is less than 0, then I know that it is decreasing at A. So basically the answer for this would be I want something that is above the x-axis and decreasing at A. Doesn't have anything about the concavity, so I drew a straight line, but like anything that's concave down or concave up, as long as it's decreasing and above the x-axis, would work. So go ahead and try to read B and see if you can figure out what that graph is being described, and then I'll kind of wrap up today's notes.
Wait, why did you draw the L-shaped thing when it's decreasing again?
So all 3 of those graphs I drew were decreasing. So when I say decreasing here, I'm saying f is decreasing.
Oh, so
there's
like
no information about concavity in A, so I don't know how it bends. So those are 3 options for the graph.
Okay.
So like in B, it tells me that f is increasing at A. If I know it's increasing as A, maybe I can do it better this way. I know that we're either increasing linearly, we can increase and be concave up, or I can increase and be concave down. So this second statement kind of tells me which concavity I choose. If f double prime of A is less than 0, then that tells me I'm using the concave down version of the graph, which would look like this. There's no information in this graph of whether you're above or below the x-axis. So I'm just going to go ahead and draw an increasing graph that is concave down. In B, I could have also reworded that second statement. If I said f prime is decreasing, it would have been the exact same graph, because again, those words and statements are interchangeable. F prime less than 0 and f double prime less than 0 and f prime decreasing are interchangeable.
So like for f double prime, like the whole like way you use it is just to figure out like how the graph like would look, or, like,
how the graph is bending, to be clear. Yes.
Okay.
So whereas if you want to summarize it in general, the first derivative tells you whether it's increasing or decreasing. The second derivative in general will tell you which way it's bending, or if it's not bending at all, basically. Is there anything else I can do a little bit better job going back and explaining? All right, so to finish out class, I know we are kind of getting towards the end of it. Your homework again, homework 7 is going to be the new homework that I've assigned. And it's just one page. You should be able to do it pretty quickly, and it's using that chart. If you have the ability to, I might recommend you print out that chart just because we will use it fairly often. But I think doing the homework will kind of get it in your head of like what it means if I say, hey, I have a function where f prime is positive and decreasing, like what that graph looks like. And that's what I want you to kind of be able to do. So that's it for Unit 1. Again, tomorrow and Thursday are going to be review days and days for you to work on homework and days for you to ask me questions. So don't try to do everything tonight unless you just feel like it. You do have several days to kind of pace out everything you need to get done. So if you're good to go, you can go ahead and sign out of this meeting, and I will talk to you tomorrow.